Oh, hi there. It's Mrs. Bertrand, and this is Limiting Reagents. Consider the following. How many burgers can be made, and which part of this scenario of burgers is a limiting reagent? So we've got 4 buns, 6 cheeses, 3 lettuce, 5 patties. If we have to have one of everything, how many hamburgers can we make? So in this case, our lettuce is going to be our limiting reagent. If a completed burger must have one of everything, I will only be able to make 3 burgers in total. That's what limiting reagent is all about. It's looking at the starting ingredients and figuring out which one runs out first. The one that runs out first limits how much product can be made. So again, limiting reagent questions are going to give you amounts of both reactants. The reactant that runs out first is called the limiting reagent, LR, and the other reactant is called the excess reagent, EX. It's important to identify the limiting reagent because the amount of product that can be made is based on it. So both in theory and reality, if you run out of the limiting reagent, it doesn't matter how much of the other ingredient you have, you aren't going to be able to make any more product because the product depends on both reactants. So we have to identify the limiting reagent so we can figure out how much product can be made. Here are the steps when we're solving these types of questions. You can go back and refer to these steps as you try each question. Step 1, we're going to calculate the moles from the mass for each reactant using our 1 mole equals molar mass conversion factor. We've done this step before. We've done it in regular 3-step problems, but this time we just have to do it twice instead of once. So that's all that's changing in step 1. Step 2, you're going to calculate the amount of moles of product using each reactant. You're doing that mole ratio. That's step 2. Again, you've done step 2 before, that mole ratio. This time you're just doing it twice. So again, you're using each reactant and you're using their moles to figure out how much product you can make. You're then going to compare how much product each of your reactants is able to make, and whichever one is the lowest, giving you the lowest quantity of product, that is your limiting reagent. You're then going to use the moles of that ingredient, the lowest one, to go back into a mass to figure out the mass of the limiting reagent. Again, mass to moles, we're using that same conversion factor that we started with, 1 mole equals molar mass. So we're going to do our first example together here. We want to know what mass of IF5 can be produced from 10 grams of both I2 and F2 according to the balanced equation below. So this particular example has 2 ingredients, I2 and F2, and we've been given 10 grams of both. You do not have to start with the same amount of both ingredients. It just so happens that that's the way this particular situation has occurred. So again, just like any stoic question, we're going to start with our balanced equation. We're going to write down what we know, what we're looking for, and then we're going to go through those steps we just highlighted. So here's our setup. We've got our balanced equation. I want to know the mass of the IF5, and again, I've got 10 grams of both I2 and F2. Again, the fact that we have both ingredients, both reactants given a mass is the identifier that this is a limiting reagent scenario. So step 1 is going to be turn both of these masses into moles. So let's set that up. So I'm looking for moles of the I2 using my 10 grams. I'm going to use my conversion factor. Moles, 1 mole equals molar mass. In this case, moles go on top. Molar mass goes on the bottom. I'm looking for the molar mass of I2. I'll remind you that that coefficient does not come into play unless I'm comparing one ingredient to another. Right now I'm just talking about I2. I want the mass for 1 mole of I2, and I've got 200, and ooh, that's an ugly 2. 253, that's an ugly 3, 0.8 grams. I'm trying to get small so I can fit everything on one slide here. Doesn't seem like it's going to be possible. Let's try it anyways. I'm up to the challenge. So the moles here is 0.0394 moles. I'm just going to do the exact same thing now, this time with the F2. So moles of F2 equals 10 grams times my conversion factor, moles on top, grams on the bottom. F2, again, I'm just looking at F2, not 6 F2s, just F2. That's the molar mass, 37.996. And that should give me 0.263 moles. All right, that's step 1. I've just done the same step as a regular stoic problem, only I've done it twice. Let's label them. as step 1. Step 2, it's the same as the step 2 that you would do for a regular stoic problem as well. I'm doing a mole ratio. So what I'm going to do is I'm going to be using my coefficients. And now what I'm looking for is I'm now going to help figure out how many moles of product I could make. But because I have 2 reactants, I'm going to use my mole ratio twice because I want to find out how many moles of product I can make from each of these starting ingredients. So let's label this step 2. I'm going to show the pathway going like this. So I'm going to start with ingredient number 1, and I'm going to use its moles to find moles of IF5. So again, I'm looking for moles of the product this time, and this is the same step 2 in a regular stoic question. I'm going to use the moles of the first ingredient. I'm going to set up that mole ratio, so I'm looking for IF5 on the top. Its coefficient is a 2, so 2 IF5s, and I want to get rid of I2, so 3 I2s will go down below. And let's do our math here. And let me see, we're getting 0.0263 moles. All right, let's do the same step 2, only this time we're going to use the second ingredient and see how it turns out. And again, I'm looking for the same thing, moles of the product, IF5, using the moles of the second ingredient now, my F2. I want IF5s on top, so 2 IF5 divided by 6 F2s, and I am getting 0.0877 moles. All right, so we are now on to the step where we're comparing how much product each of these reactants are able to make. So reactant number 1, I2, is able to make 0.0, sorry, that decimal looks like it disappeared on me, 0.0263 moles. And if I looked at reactant number 2, my F2, it's able to make 0.0877 moles. So here I'm looking for the least amount. Remember that the thing that runs out first is the limiting reagent. And so the one that makes the least amount of product is going to trace back to our limiting reagent. So the products here, the moles here, from the I2, that is the smallest amount. So that means that my I2 is my limiting reagent, and my F2 is going to be in excess. Again, just those short forms that we learned from the very beginning of our lesson. So this is now where I've starred. We're going to do one last step. We want to turn that IF5 number of moles from the limiting reagent. That's the moles that I've just circled here. That's the moles of IF5 using the limiting reagent. We have one additional step. We're going to take those moles, we're going to turn it into mass. So again, same 3 steps as a regular stoic problem, only the first 2 steps get repeated for each reactant. But at this stage, now that we've identified the limiting reagent, we're going to use those lowest moles to do the last step, that moles to mass conversion. I'm just going to do that on the next slide here, since I'm out of space. So this last bit, let's call this step 3. We're taking the mass of, actually let's label it. This is the mass of IF5, our product that we're doing in the last step. We're using the moles we found in step 2, the lowest value. We're using our molar mass on top this time. Same conversion factor as always, 1 mole equals molar mass, but we're just going to flip it so we can get rid of the moles here. And we are getting a grand total, going back to 2 significant digits here, 5.8 grams. All right. So again, just a quick notice that finding the limiting reagent is not as simple as which reactant is less. The mole ratio must be used to determine how much is needed because of those coefficients. So again, 3-step problem, only the first 2 steps get doubled. Let's try another example. This is tricky business. Example number 2, how much Li2O, so lithium oxide, in grams can be produced from 3.5 grams of lithium and 4.5 grams of oxygen. I've given you a balanced equation to start with. And again, you'll notice this time, instead of the same quantity of reactants for each one, I've given you different quantities. This does not change the problem at all. We start with our balanced equation, we write down what we know, we write down what we're looking for. Just like the last time, the identification that this is limiting reagent is the fact that you have reactants, two reactants, and they both have numbers. So when you have two numbers like this, that's identifying this as a limiting reagent question, which means you do the first two steps of stoich twice and the last step once. So let's get to it. Step number one, we have to do this twice over. We are looking for moles using the mass. I can't make a dot. There we go. And my molar mass is going to be on the bottom this time. So again, I'm using that same conversion factor as always. 1 mole equals molar mass. I've got 1 lithium. We do not incorporate the coefficient. So 6.941 right off our periodic table. And we're getting 0.504. Seriously, the dots. Moles. All right. Let's do it for O2. So moles of O2 are equal to 4.5 grams. Moles on top, molar mass down below, and we should be able to get 0.141 moles. Here's step one. Step two, I'm just going to take each one, I'm just going to make some space below. I'm going to take each one and I'm going to use these moles to find moles of product. So in each case, I'm going to look for moles of lithium oxide using the moles of each ingredient. So the first ingredient I'm going to do is the lithium, and then using my conversion factors, I've got 2 lithium oxides for every 4 lithiums. So that first one, we're going to have 0.252 moles. Let's call this step 2 so we can keep track of it a little better. We're going to do another step 2 over here, just making some space. Same step. I'm going to look for the moles of product, Li2O, but this time I'm going to use the moles of ingredient number 2, my O2. And so I'm going to have the same top conversion factor, my 2 Li2Os, but my O has nothing in front, so there's only a 1 O2 here. So my answer on this one is going to be 0.282 moles. Is that right, or is that a 6? 282. All right. At this point, we're doing our comparison. So which moles is the least? That's going to trace back to our limiting reagent. We're going to compare 0.252 and 0.282. 0.252 is the smaller value. So this is the limiting reagent. And tracing it back, that means that value is from the lithium. So we can put an LR there. That means by default, oxygen is in the excess. Now, it just so happens the last two examples had the first ingredient as the limiting reagent. Is that always going to be the case? No, it's just coincidental. It could be either ingredient that's going to run out first. Now that we've identified which one makes the lowest moles, again, I now have an additional step. I'm going to take the moles that I've circled and starred. That's how many moles of product I can make maximum, and I'm going to use that many moles to convert back into mass, my last step. So step number 3, I'm looking for my mass of my product, my lithium oxide. We can label it there if we like, using the moles that I found in step 2, the lowest value. Oh my gosh, why can't I make a dot? Seriously. We've got our conversion factor, molar mass on top. Seriously, the dots are going to kill me. And 1 mole underneath. Moles are going to cancel here. And that's going to leave us, bringing it back to 2 significant digits, 7.5 grams. Dun, 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 dun. So there's one more thing that we sometimes calculate with a limiting reagent question, and that is how much excess of the reactant that we don't use, how much is left over. Because if we have 2 reactants and we use the limiting reagent all up, we consume all of it to make product, the excess means there's going to be some leftovers. So sometimes the question says, how much leftover do you actually have? So this is a 3-step question. Let's go through the steps. And again, I want you to go back to these steps and refer to them when you're tackling this question. It will help. Step 1, calculate a mole ratio between the 2 reactants, looking for the moles needed of the excess reactants. So you're going to look for the moles of the excess. So even though you have the moles of both from step 1, you're going to do a mole ratio looking for the moles that you need of the excess. In step 2, you're going to subtract the needed value of moles from the amount you actually have. So the original mole calculation. So looking at how much do you have versus how much do you need. So in the first step, you actually calculated how many moles you need of the excess, and then you're going to subtract what you actually have minus how much you need. The difference is your leftover reactant. And then finally, you're just going to take those moles and you're going to calculate the mass. Again, using Old Faithful, 1 mole equals molar mass. All right, so we're just using the last example that we did. So we had the 2 masses given, and I'm not going to show the calculation because we already did it, but I just want to get us to the point where we remember the moles of each one. So we had the moles of this ingredient as 0.504 moles. Same calculation we did the last time. I'm just going to not repeat it because we already did it. And this one we had was 0.141. So what we just wrote down are how many moles we have of each of the given ingredients, the Li and the O2. But what we're going to find out next is how much we actually need of the excess. So let's label the 2 parts that we had before. Remember that we had identified the Li as the limiting reagent and the O2 as the excess. So everything on the screen right now is from the previous question. Now we're going to get into the new stuff. And our target, our focal point is the excess. So our focal point for this part of the question is actually the O2. So in the second step, we've actually done the first step already. We're just transitioning those mole values into our question from the first part. The second part, though, we're going to look for the moles of O2 using the moles of the Li. And this is where it's confusing, because you might be saying, lady, we already know the moles of O2. It's 0.141. What we're doing in this step, though, is we're going to see how much O2 we actually need if we use up all of the Li. So we're going to use all of the 0.505 moles of lithium. We're going to do a mole ratio. So we're going to have my 1 O2 on top, my 4 Li's on the bottom. And what we're getting an idea of here is we're getting a mole value, and our value is 0.126. This is how much oxygen we actually need. So remember, the O2 is in excess, so I'm going to have some leftovers. So what I just figured out is by using up all the moles of the Li, knowing that I'm going to use all of those up, that's what limiting reagent means. It means I'm going to use all of them up. If you think about all those analogies we've done with the hamburgers and the hot dogs and all the rest of it, I'm going to use up all of the limiting reagent. This mole ratio shows me how much of the O2 I'm actually going to need to partner with it. So I'm going to need 0.126 moles. Therefore, the amount left over, or the, let's say, leftover excess O2 is going to be the difference between what I have and what I need. Let's do it in gray. 0.141 moles, this is what I have, minus 0.126 moles, which is what I need. Therefore, my leftovers is 0.0149 moles. So I don't have a ton of excess, but I do have some. That's the hardest bit of this question. The last step, I'm just going to take those moles that I just found, and I'm just going to convert them back into a mass. We know how to do that using our 1 mole equals molar mass. Let's do it over here. So the mass then of our excess, in this case our excess, remember, is O2, using the moles we just found, the leftover moles. If I can make a dot. There we go. And I've got an O2 molecule, so 31.998 grams divided by 1 mole. We'll get rid of our moles here. My final answer is 0.48 grams. Dun, 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 dun. So this is a really good question to try on your own. It's a whiteboard question, so we'll be doing this together in the classroom. I'm not going to take this one up in this video because we're going to do it in class as a big wrap-up. But again, you're going to go through the different steps. So the first thing I'm asking you to do is to figure out which one is the limiting reagent. Then you're going to find the mass of CO2, so that's the unknown. and then you're going to calculate the mass of the excess reagent that's left over. So you're going to do all the bits. All right? Have fun. And then finally, you're going to do some homework, and homework has two parts. We have some warm-up questions on page 309 and some more challenging questions on page 311. And you know what to do. Have fun with it.